Good evening, Wincham. Yes, this is the end of everything. A long time ago, I wrote a talk called The Beginning of Everything, which explained where the universe came from. But after giving that talk a few times, people kept asking me, yeah, but what about the end of everything? So I ended up writing this talk. And as you can see from the subtitle there, I'm going to be talking about the fate of the Earth and the fate of the Sun and the galaxy, and ultimately the fate of the universe. So if you'll excuse me paraphrasing Buzz, we're going to eternity and beyond. So I'll be giving a little prologue and talking about the future of what's going on locally in the solar system, the future of what's going to happen within our galaxy, stars, our galaxy and other galaxies, and ultimately the fate on the long term into the far distant future. We'll just see how far we can go. And then, so as you're not left totally depressed, I'll finish with a slightly more upbeat epilogue. So I'm not going to cover the other talk that's the sort of bookend to this, the beginning of everything, but just a very brief synopsis. The universe started 13.8 billion years ago. It inflated until it was about the size of a golf ball with dimples, which eventually, when the universe expanded, became the cosmic microwave background. And that's sort of how we know that the Big Bang Theory is a fairly good explanation of how the universe came to be, because we're getting all sorts of observations like the amount of hydrogen in the universe and the cosmic microwave background, as well as the large-scale structure of the universe, roughly right. But in this talk, we're talking about where we're going in the future from 13.8 billion years onwards. So in effect, we're resetting the clock. And in order to keep track of where we are in time, I've got this timeline running along the top. And a red rectangle is going to move from one box to the next. Each box represents 10 times further into the future. So as we go into the future, maybe 1,000 years, 10 to the 3, 10 to the 4, 5, 6, a million years into the future, 10 to the 9, a billion years, and so on, 10 to the 12, a trillion years into the future. And I'm indebted to the work of Adams and Laughlin, who published a paper a quarter of a century ago, in which they laid out calculations of the timescales on which various astrophysical phenomena are likely to happen. And I've used that paper to try and get all my slides in the right order. Regardless of whether I'm talking about the Earth or the Sun or the galaxy, I'm literally going through one step at a time from left to right there. So I'm not going to bother with the next 100 years or the next 1,000 years. Let's assume we get climate change under control. Let's assume we don't end human civilization in nuclear war. We know things are going to happen on timescales of 10,000 years into the future, because we know, for instance, that the Earth's axis is precessing on a timescale of 26,000 years to do one complete circuit. So on a timescale of 10,000 years or so, the Earth's axis is going to go from pointing in one direction to pointing, roughly speaking, in the opposite direction. The Earth's axis points to a point on the sky which rotates in a large circle in 26,000 years. Currently, we have the North Pole there, very close to Polaris, within a degree or so. But in another 10,000 years, the Earth's axis is going to point over here, much closer to the star Vega. So that's going to make it a lot easier for Boy Scouts to find which way is north, because they'll be looking for a bright star rather than a magnitude 2 star. So 5 times brighter, it's going to be easier to find north. But one of the consequences of the Earth's axis pointing in a different direction is that at the moment, we are nearer to the Sun in perihelion in January during northern winter. But if the Earth's axis is pointing in the other direction, then we're going to end up being closest to the Sun during northern summer. So instead of mitigating the seasons, it's going to exaggerate the seasons because of that small difference in distance as well as the tilt, acting in concert to produce more extreme climate. Any variation in the Earth's climate, which is a result of either the Earth's axis or the Earth's orbit around the Sun, they're collectively known as Milankovitch cycles, and we'll hear that again shortly. On a timescale of about 10 to the 5 years into the future, the Voyager spacecraft that launched back in the 1970s, the late 1970s, Voyager 1 visiting Jupiter and Saturn, and then Voyager 2, Jupiter, Saturn, Uranus, and then Neptune, using gravity assists to go past the planets. They're heading out of the solar system on a timescale of 10 to the 5, somewhere between 10 to the 4 and 10 to the 5 years. They'll be passing through other solar systems. So at the top there, Voyager 1 is going to head off and pass through the solar system known as Gliese 445. At the bottom of the picture, Voyager 2 is going to head off in a different direction and is heading towards Ross 248. Again, they'll be passing through those solar systems. Pioneers were launched earlier but are not going as fast. But Pioneer on the right there, whoops, sorry. Let's back off. Pioneer on the right, Pioneer 10, is heading off in the direction of Aldebaran, and Pioneer 11, heading off on the left of this picture, is heading off towards the centre of the galaxy. Still on a timescale of 10 to the 5 years into the future, we know that ice ages have come and gone in the past on timescales of order 100,000 years. And only relatively recently has the Earth entered a so-called interglacial, a warm period in between ice ages. Therefore, we can predict that the Earth is going to be subject to another ice age in approximately 100,000 years or so. Again, this is another manifestation of the Milankovitch cycles due to changes in the Earth's orbit around the Sun.
Is that notwithstanding the climate change?
That's going to happen regardless of what we do. Yes, we're still going to have an ice age, yes. We know that the Earth is slowing down. In the last few years or so, amazingly enough, the Earth has been speeding up. The rate of spin of the Earth has been slowing down for a long, long time, but for some reason or another, for the last few years, it's been speeding up. But on a long enough timescale, it will definitely slow down, simply because the Earth is being robbed of its angular momentum by the Moon. The Moon is raising tides. That is taking some of the angular momentum of the Earth and transferring it to the Moon. So in past decades, we've added a leap second every once in a while. We haven't done so for quite a while. We've added a leap second, usually on the 31st of December at midnight, and a leap second has been added every few years to keep our clocks synchronized with the rotation of the Earth. Weirdly, the Earth has been speeding up recently, which means maybe we have to take a leap second out of the clocks. But that's never been done before, and so people are very reluctant to remove a second from every time clock in on the surface of the Earth. But we know on a long enough time scale the Moon will continue to slow down the Earth, and in another 100,000 years or so, instead of adding a leap second every few years, we would need to add a leap second basically every day. The rotation period of the Earth is likely to be about 24 hours and a second. So we would need to add a leap second every day to keep clocks synchronized with the Earth's rotation. We know some stars are going to die on timescales of order 10 to the 5 years or so. We can't tell exactly when any star is going to go supernova. This is definitely a candidate, Eta Carina, in the middle of the Eta Carina Nebula. For the last few thousand years, it's been sloughing off its outer atmosphere. It's a very massive, very unstable star, so it's definitely a good candidate for a supernova. It's produced this nebula as a result of the outer layers of the star being sloughed off for many thousands, if not tens of thousands of years, and so it's definitely primed to be a supernova, but we still can't predict exactly when that's going to happen. It is thought that it will happen in the next 10 to 100,000 years, but we can't tell when. It might be beaten to the punch by Betelgeuse, which will be more spectacular for those of us in the Northern Hemisphere. It's going to completely ruin the constellation of Orion, of course, if it does go. This is a picture of night sky taken over Prague, in which Betelgeuse has been artificially brightened to give us an idea of what it will look like when Betelgeuse decides to go supernova. It'll be bright enough to probably visible during the day, as well as being a spectacular sight at night. But it's not just supernova that we have to worry about in terms of the radiation from supernova. At the distance of Betelgeuse, that's probably not going to be a problem. But there are other star systems which could, in principle, produce more radiation here on Earth than, for instance, Betelgeuse or Eta Carinae. Wolf-Rayet stars, this is Wolf-Rayet 104, at least an artist's impression of Wolf-Rayet. Some of these stars have very high rotation systems and can produce jets. So even though this one is 7,000 light years away, when it dies, it's thought that this might produce radiation that could pose a threat to the Earth if the jet happens to be lined up with the Earth. Most of the radiation when this star dies is probably going to get funneled into the jets. It might end up being something like a gamma ray burst, which at a distance of a few thousand light years will be a significant dose of gamma rays. So it's probably going to be a problem. We don't really understand the mechanism by which these jets are produced, but if this star decides to die and those jets are pointing in our direction, that could well be a problem for Earth. But given there's nothing we can do about it, we just have to keep our fingers crossed and hope that that jet is not pointing in our direction. On a timescale of about 10 to the 6, 1 million years into the future, stars are all orbiting around the Milky Way. They're being mapped at the moment by, or just recently been mapped by the Gaia spacecraft, which has just finished its mission. So we've been looking at a lot of stars in our neighborhood, how they're all moving around the center of the galaxy in essentially independent orbits. But because none of those orbits are exactly the same and they're not all circular, that means some stars will sometimes get a little bit closer to others as we all jointly rotate around the center of the galaxy. And it's been calculated that at least one star is going to get very close to us on a timescale of about 10 to the 6 years. Gliese 710 is going to come close enough and then drift away again, such that it will actually enter our Oort cloud. So the Oort cloud is all of the icy bodies that are gravitationally bound to the sun, but when this star comes into our solar system, it's going to gravitationally disrupt a huge number of icy particles, and some of those are going to rain down into the inner solar system. So we are going to end up with loads of bright comets coming our way, possibly naked eye comets every month for 1 million years when this star comes close enough to disrupt our Oort cloud. It's interesting to note that for a while, during this period of many hundreds of thousands of years, our solar system will actually have 2 stars in it, much like other planets and moons that we all know and love. So, 10 to the 6, Meteor Crater, perhaps you recognize it, Meteor Crater, Arizona. Does that mean we can expect an impact like this every 1 million years? Well, no, not really. I'm showing this image, one, because it's amazing, isn't it, how lucky we are that it just missed the visitor center there. But also, 10 to the 6 is not the expectation for how often we get an impact like that. It's a reminder that any impact that's older than about 1 million years will probably be eradicated by the weathering systems in the Earth's atmosphere. Simply changes of temperature and wind and rain and freezing water, etc., will tend to weather and erode any sign of impact. So we've probably had these impacts for billions of years, but we only can see, generally speaking, the more recent ones because the old ones get eroded. That's of course true on a planet like the Earth with an atmosphere, but you might say, yes, but the craters on the moon don't get eroded because there's no atmosphere there. Well, true, it's no atmosphere, but it doesn't necessarily mean they don't get eroded. If you think about, for instance, the footprints on the surface of the moon is constantly being bombarded with micrometeorites. So it's not weathering in the sense of the Earth's atmosphere, but the moon is getting pummeled with micrometeorites all the time, and hence the footprints of the astronauts on the moon are going to be eradicated over a period of time. Even all the Apollo hardware will eventually get pulverized by micrometeorite impacts if you wait long enough. Sooner or later, all evidence of the Apollo landings will be eradicated. 10 to the 7 years into the future, 10 million years into the future. What's happening to Pioneer? We've already said that it's flying out of the solar system like the Voyager spacecraft, and on timescales of 10 to 100,000 years, it'll be passing through other solar systems. But on a timescale of 10 to the 7 years, the plaque, which tells people where it came from, will ultimately become unreadable. The Pioneer spacecraft is flying through the interstellar medium, and the plaque is going to get eroded and pitted simply from flying through a medium which is not a perfect vacuum, but is full of microscopic dust particles, little bits of carbon and silicon, and therefore, over millions of years, that pitting is ultimately going to make the plaque unreadable. So if this spacecraft is picked up in the next few million years or so, having passed through solar system after solar system every 10 to 100,000 years, so it might have passed through dozens, hundreds or more solar systems and might get picked up by another civilization, they can read the plaque and figure out from the pulsar map where it came from and figure out that it looks like it came from the third rock from the sun in that particular solar system. But if anybody picks it up after about 10 million years or so, it's going to be impossible to read the plaque, and so nobody will be able to figure out where this particular piece of junk actually came from. 10 to the 8 years into the future, we can ask ourselves what's going to happen in terms of changes within our solar system. So we can ask ourselves, for instance, what's going to happen to Saturn's rings? But before we ask what's going to happen, perhaps we ought to ask the question, well, where did they come from in the first place? Was it a pulverization of a moon similar to Titan, for instance? Similar to Mimas, as we've got here. Was it a pulverized moon that actually produced the debris which produced the ring system? That's thought to be one of the most likely reasons that the Saturnian ring system came about. When we look at a moon like this, we may look at the moon and think to ourselves,
that's no moon, it's a space station.
Because it does bear a striking resemblance to the Death Star with this very large impact crater here called Herschel. But it is thought that if you take something with about the mass of Mimas and pulverize it, if you run a simulation and ask what would happen if you took a body like Saturn without a ring system, took a moon like Mimas, pulverized it and just waited, what will happen? You often assume that, well, you'll generate a cloud of dust from pulverizing Mimas, but that cloud will simply go round Saturn, much like the original moon did. But actually, when you run the simulation, you get a surprising effect of, look at the timescale. In a matter of days, you end up with a ring system, because if the pulverized dust that you generate is all interacting with each other, they don't all go round independently and stay on their orbits. They all interact with each other and slowly start to spread out over the entire orbit and generate a ring system. And all of these individual particles, although they are in principle orbiting independently, they are all very slowly spiraling inwards. And if you wait long enough, they will form the very familiar ring system that we now know and love. So it's thought that this happened quite a few million years ago. And the question is, has it now stopped? Is it now stable? And the answer is no, it is still evolving. All of those individual particles in the Saturnian ring system, some of which are being shepherded by Saturn's moons, they are still spiraling inwards, and particles on the inner part of the ring are basically raining down on the surface of Saturn. So if we wait long enough, and it's been calculated that if we wait on time periods of order 100 million years or so, all of the particles in the ring system will have spiraled inwards, rain down onto the surface of Saturn, and the ring system will be no more. So for those of you who like to see Saturn through a small telescope, get in now, because in a few million years' time, it will not be quite the same sight it is at the moment. One thing we have to remember about the solar system, again when we're thinking on timescales of 10 to the 8 years into the future, is that the solar system, although we tend to think of it by looking at a clockwork orrery or a little tellurian showing how the moon goes around the Earth and the Earth goes around the sun, we tend to think of the solar system as being clockwork. We have an app on our phones that can tell us where the planets will be in 1,000 years, or where they were, for instance, at the birth of Christ, to try and work out what the Star of Bethlehem was. We get fooled into thinking that we can go an arbitrary distance time into the future or the past and work out where the planets were. But the solar system is actually chaotic. We tend to think of it as clockwork and well regulated, and we can calculate the precision we want for the distance to the moon or where Jupiter is in its orbit, but actually, no, they're chaotic. We can calculate where they're going to be on short timescales, but on a timescale of hundreds of millions of years into the future, we don't even know how many planets there will be in the solar system, let alone where they will actually be in their orbit. It might be that Jupiter decides to eject some of the smaller objects in the solar system. There have been planetary rearrangements in the past. It is very probable there will be planetary rearrangement in the future. Just because things look nice and stable now doesn't mean they'll remain stable on these sorts of timescales. Still on timescales of order 10 to the 8, 100 million years into the future. We know that's, roughly speaking, the length of time it takes the Sun to do one circuit of the Milky Way. So there's where we are at the moment. We are sitting in between two of the major spiral arms of the Milky Way. That means we're in a relatively low density part of the Milky Way in terms of how many stars, how many neighbors do we have. But as we rotate around the Milky Way, as the Milky Way rotates, it's been calculated that on this timescale, we are going to end up inside one of these spiral arms, rather than being sitting in between two spiral arms. which means we're going to have a much higher stellar density. We're going to have many more neighbours. If you work out how many stars are within, let's say, 10 light years of us at the moment, it's only a small number. But perhaps at this timescale, we're going to find the number of stellar neighbours goes up quite considerably. So what's the consequence of having a lot of stellar neighbours compared to the number that we have at the moment? Well, one of the consequences we've already mentioned, because we know what's going to happen when Gliese 710 gets close. It'll disrupt the Oort cloud. We'll end up with a whole load of comets coming our way, and that will increase the likelihood of a planetary impact with Earth. So when we're in a spiral arm, we're likely to find a higher incidence of objects hitting the Earth. And when we look at a historical record, how often have species been exterminated from the face of the planet? How often have we had an extinction level event? We see that the number of extinctions is spiking, and we've had quite a few of these spikes over 500 million years or so. That's not proof that we're necessarily going to have a problem in 100 million years, but it does indicate that these things are not absolutely periodic, but they do come round on these sorts of timescales. The last one on the right-hand side, the KT, is at the boundary between the Cretaceous and the Tertiary era. That's the one that killed all the dinosaurs. Just as well for us, that allowed us, the small mammals, to come out during the day and start to evolve into the people we are now. So it looks like on this sort of timescale we can expect another extinction level event. This, of course, is just an artist's impression of a very big rock heading towards the Earth. It looks like it's heading towards Italy. Okay, that's bad news for Italy, but of course if the rock is big enough, it's going to be bad news for the entire planet. It'll be so disruptive, it will result in species being exterminated. The only real question is, will one of those species include us? We've got a little bit of time to figure it out. Hopefully we're not going to have such a massive event for quite a while, and we've got plenty of years to figure out what are we going to do if one of these big rocks comes our way. But a second reason that it might be a problem to have lots of stellar neighbours is that at the moment there are no massive stars close to us that are likely to go supernova. The closest is hundreds of light years away, which is not a problem. But if we have lots of stellar neighbours on this timescale, maybe one of those neighbours will be massive enough to be a supernova candidate, and then that could be a problem. It's been calculated that a supernova within 100 light years of Earth could be a serious danger to life on Earth because of the amount of radiation that will be produced when it goes supernova. It's been calculated that if a supernova goes supernova within 20 light years of Earth, that could easily sterilize the planet. That gives you an idea of the gamma ray produced by a supernova. So it's something that we sort of have to worry about, but again, there's not an awful lot we can do about it in the sense that we can't choose our neighbours. We just have to hope that none of them are going to be massive enough to be supernova candidates. But we know it has happened in the past. There is evidence that we have had, in historical past, supernova go off relatively close to Earth. Any supernova within 100 light years, in principle, produces enough of a particular isotope called iron-60. It produces this radioactive isotope, and as far as we know, there's no other way of making it, and it has a half-life of various numbers of millions of years. Iron changes into cobalt, which then changes into nickel. But we have found that isotope in the Earth's sediments. If it's got a half-life of a few million years, it can't have been there since the Earth was made. It must have arrived more recently if it's got a half-life of a few million years, and yet we find it in the Earth's sediment. So the fact that we do see it in small quantities in Earth sediments tells us that this, as far as we know, can only be manufactured in a supernova. So if we find it on Earth, something relatively close, if it was distant, we wouldn't get that much material deposited. It must have been of order 100 light years or so in distance, or at least within 100 light years.
So that's been something that killed off from the
yes,
previous...
indeed,
Right.
indeed. We can't pin it down necessarily in terms of time, but there is evidence that that might well have been the case. So if it's happened before, the point is we know it's happened before, possibly more than once over the last few billion years. It's quite likely that it will happen again. On a timescale of 10 to the 8 million years, For all of this time, the moon has been robbing the Earth of angular momentum. The moon has been raising tides and slowing the Earth down, and the moon has been slowly moving away from the Earth as a consequence, stealing the angular momentum of the Earth and using it to move away from the Earth. The length of the day at this point has been calculated after 100 million years or so to be 25 hours. So there is no point now thinking about adding leap seconds to try and keep your watch synchronized with the rotation of the Earth. It would be crazy to keep adding leap seconds indefinitely. At some point, we would just have to give up the idea of 24 hours in a day. Perhaps this is the time we ought to decimalize and actually go to 25 or 100 hours in the day or something like that. But because the moon is moving away from the Earth, at some point it'll be such that the distance from the Earth to the sun will be great enough that it will never be possible at any point from this point onwards to have a total eclipse of the sun visible from the surface of the Earth. At the moment, we're lucky enough to have the disk of the moon just about the right size to cover the disk of the sun. If the moon moves further away, it will never be able to fully cover the disk of the sun. We can still get annular eclipses, we can still get partial eclipses, but we will never again get a total eclipse from the surface of the Earth. So again, for those eclipse chasers amongst you, get in now, because in another billion years or so, it will simply not be possible, or at least it'll be much more expensive because you'd have to leave the surface of the Earth in order to see a total eclipse of the sun. Still on a timescale of 10 to the 9 years into the future, a billion years or so. A second consequence of the moon moving further away, apart from the fact that we lose the spectacle of a total eclipse, perhaps more dramatically, is the moon has been stabilizing the tilt of the Earth. The moon is coupled in an angular momentum sense to the Earth, and that is partially responsible for keeping the Earth locked in at 23.5 degrees. Historically, it looks like the tilt of the Earth hasn't changed much from 23.5 degrees, not by more than a degree or so, for a long time. And we think that's because of the location of the moon. If the moon moves further away, it's calculated that it will no longer pin the Earth down to that particular tilt, and the Earth's axis would be then free to be pulled backwards and forwards by other planets and perhaps act a little more erratically. There's no reason why in principle it couldn't go vertical or even horizontal, and that of course would cause chaos to the seasons. So on timescales of 10 to the 9 years into the future, we have to forget climate change. Climate will be something that changes erratically rather than something that we can see changing year by year, decade by decade, millennium by millennium. On a timescale of still 10 to the 9, Voyager's gold disk will become difficult to read, if not impossible to read. Remember, for Pioneer, that happened after 10 million years or so. Voyager's gold disk will last perhaps 100 times longer. And one of the reasons for that is that the gold disk, the phonograph, which contains greetings from Earth and music and various other things, that's actually protected behind a cover. And that cover is going to get rather pitted and corroded as it flies through the interstellar medium and has impact with all of this interstellar dust. So the disk will be protected by the cover, which will end up completely unreadable. And that's a bit of a shame because the cover contains the instructions for how to read the disk. Here's the instructions. It says, where did this object come from? Again, a pulsar map to give you the original coordinates. And here is encoded the instructions of what the hell this thing is and how you play a long playing record, because it's possible that aliens don't know what an LP is. So you have to tell them that you put a stylus in the groove, you turn the record at a particular speed, and then you will hear sounds, and that will be the sounds of Earth saying hello. So after 10 to the 9 years, again, remember Voyager will have passed through solar systems every 10 to 100,000 years. So after 100 million years, it probably will have already passed through thousands of different solar systems. If one of those solar systems pick it up and read the instructions, they'll be able to play the record and they'll say that's what Earth sounds like. If it's not picked up until after this period of about 1 billion years into the future, then, although in principle there might be something left of the Voyager spacecraft, the chances are there'll be very little left and they will not be able to read the disk, either the instructions nor read the sounds, play the sounds recorded thereon. Shame. This is the point at which the sun is starting to change. 1 billion years into the future, it's not a red giant yet, but the luminosity of the sun will slowly start to change as the amount of hydrogen in the sun's reserves starts to drop. And over a period, as it approaches its red giant phase, the luminosity will increase by something like 10% every billion years. So over a few billion years, the sun's luminosity is going to increase, and that's going to drive the surface temperature of the Earth uncomfortably high. You think it's been warm the last week or two? No, it's going to be something like 80 Celsius across the Earth. The oceans are going to boil dry, and there's going to be nowhere you can go. Going underground is not going to help. If you want to survive, we'd have to temporarily leave Earth until it cools off a little bit. And in terms of cooling off, we know the sun is going to go through a red giant phase, again in a few billion years or so, heading towards 5 billion years. And the surface of the sun is going to grow until it's at about the same position as the orbit of the Earth. And you think, oh, yeah, that surely is going to be a little bit of a problem for us, isn't it? Some people say the Earth is going to get engulfed because the red giant that we can calculate for a star, the mass of our star, a red giant ought to be a little bit bigger than the orbit of the Earth. But actually, it's not known whether or not the Earth is going to be engulfed or not. And that's simply because if you take this cartoon on the left where nothing is to scale, the Earth won't necessarily be engulfed, because as the sun starts to grow, it's going to go through a red giant phase, and that produces very strong solar winds. And those solar winds will carry a fair bit of mass away from the sun. The sun will lose mass towards the end of its life. And if it loses mass, that means it's going to lose the tug of gravity on the Earth, so the Earth's orbit is going to increase. So as we go through this little cartoon, as the sun grows, the Earth is actually going to move away from its original position. So yes, the sun will engulf the Earth's orbit in the sense of that's where the Earth used to be. But by the time it gets there, the Earth will have moved into a new orbit, perhaps out somewhere where Mars is now, for instance. So yes, the sun will go through a red giant phase. Yes, the sun will get big, but it doesn't necessarily mean the sun will engulf the Earth. Maybe the Earth will survive. Let's assume it does for the sake of argument and see where we go next. After the sun has been through its red giant phase, it'll slough off its outer layers, produce a rather nice planetary nebula, no doubt, and what's left will be a white dwarf, possibly with some solid carbon at its core. But bad luck comes in, well, usually more than one phase. So if we can survive the sun going through a red giant, we have another problem to contend with. And that is the Earth is going to lose its magnetic field, here on a timescale of many billions of years into the future. The Earth has a magnetic field because we have a molten core. Molten metal spinning gives you a dynamo, generates a magnetic field. But the Earth's core is molten not because of any heat coming from the sun. The Earth's core is molten because of radioactive decay of elements that have been there since the beginning. For 4.5 billion years up till now, 10 billion years if you go to the point at which the sun becomes a red giant. That radioactive decay of elements, iron and nickel and other materials in the core of the Earth, various radioactive elements, are dumping energy into the core and keeping it molten. But eventually, the radioactive decay is not going to be enough. It'll fall away because there's a finite half-life to all of this radioactive decay. Eventually, there will not be enough heat generated to keep the core molten. The core will solidify, and when it does, you don't have a dynamo. When you don't have a dynamo, you don't have a magnetic field. So the Earth is going to lose its magnetic field, which means we're then going to be exposed to radiation from the sun and the cosmos. Perhaps the sun is not going to be such a problem when it turns into a white dwarf, but we are going to be then irradiated with cosmic rays. It's thought that maybe this is what happened to Mars. Mars is a smaller planet, so perhaps its core solidified a long time ago compared to what the Earth's core is doing. If Mars had a core that solidified a few billion years ago, or many hundreds of millions of years ago, if its core solidified, it would have lost its magnetic field, it would have been subject to strong radiation. Maybe that's why it lost its atmosphere. So it's the fact that Mars is a smaller body that meant it cooled faster, which meant it lost its field and then lost its atmosphere. That's still hypothetical, but that's what some people believe. And given that bad luck comes in threes, if we survive the sun going through a red giant, if we survive the loss of a magnetic field, we then have to deal with the fact that we're going to crash into Andromeda, or at least Andromeda's going to crash into us, depending on how you look at it. So for those of you who like astrophotography, if you wait a while, you don't have to use a telephoto lens to see Andromeda. A wide-angle lens will be big enough as it comes hurtling towards us. The two galaxies are going to pass through each other on timescales leading up to about 10 billion years or so. The two galaxies will pass through each other. Probably no stars will collide, but all of the gas and the dust is going to get churned up and lead to a riot of new star formation as the two galaxies eventually settle down. It'll take a little while for them to settle. Eventually, we're going to have two nuclei in this new merged galaxy. The original supermassive black hole at the center of our galaxy and the supermassive black hole at the center of Andromeda are going to orbit each other for possibly a few billion years before they eventually spiral towards each other and merge together on a much longer time scale. But given that stars don't collide with each other, I'm sure we can survive this. If we can survive the sun going through a red giant phase, if we can survive the loss of a magnetic field, I'm sure we can survive the collision with Andromeda. If the sun gets pulled out of the Milky Way, the planets will just go with it. It's going to be a relatively slow crash. If you look at the timescale, it takes hundreds of millions of years for the crash to take place, and so if the sun gets pulled out, the planets will simply go with it. So I'm sure we can survive that. On a timescale of 10 to the 11 years or so, the slow dance between the Moon and the Earth finally comes to a rather graceful end. At this point, one day will be the same as 1 month. In other words, the length of time it takes the Earth to rotate once will be the same as the length of time it takes the Moon to go around the Earth. The Earth will have slowed down, and 1 month equals 1 day means that as well as one face of the Moon always facing the Earth, which it does at the moment, we will find one face of the Earth is always facing the Moon. So in other words, from particular points on the Earth, you will always see the Moon in a fixed point in the sky, much like if you were to land on the Moon and look up, the Earth is always in the same place in the sky. There are some points on the Earth in which the Moon will never rise. The two are locked together and always facing each other as they go around, much like Pluto and Charon are doing at the moment. And although that looks like a little bit of a Photoshop, that is a genuine picture of a full Earth and a full Moon. Bear in mind it's the far side of the Moon because the picture is being taken from some distance away, so we're seeing a full Moon where this is the far side rather than the more familiar near side. This was taken by Deep Space Climate Observatory. So we're getting towards the end. Our red rectangle is moving towards the right-hand side of the bar at the top there. If we get to 1 trillion years into the future, what's going to happen to our local group? I've already said that we've got a Milky Way in the middle there. It's surrounded by lots of satellite galaxies. There's dozens, if not hundreds, of small satellite galaxies around the Milky Way. And we've already said that in terms of members of the local group, we know that the Milky Way is going to collide with the Andromeda galaxy. Sooner or later, the Triangulum galaxy is going to get in on the mix as well. And indeed, the mega galaxy that results is basically going to hoover up everything in the local group. So everything that is currently gravitationally bound in the local group within a few million light years of the Milky Way, everything is going to end up in one mega galaxy. M31 and M33, the Triangulum galaxy, they'll end up as one big galaxy. It won't actually be a spiral galaxy. That's just a little icon I put in the middle to remind you that everything gets merged together. And we can ask ourselves what's going to happen to galaxies further away than the local group. Well, we already know, this is a talk I gave a little while ago during COVID. I got bored from having lockdown and decided to try and image a very remote object, not with a telescope, but just using my camera on a tracker. And I managed to pick up a galaxy, a quasar, in other words, a galaxy with a very bright nucleus. And even though that galaxy was receding from us at twice the speed of light, it's still possible to image these very distant galaxies. So the expansion of the universe has been going on for 13.8 billion years, and as far as we know, it's going to continue. I'll get to that point in just a second. But even though we know that objects are receding from us at superluminal speeds, we know that it is still possible to get the light from these galaxies. I've done that with my camera, and of course the Hubble Space Telescope has been taking pictures like this deep field. This one is the ultra deep field. And when we look at very distant galaxies, quite a number of those galaxies are at such huge distances, those galaxies are receding from us faster than the speed of light. It's only arguably the closer galaxies that Hubble sees that are actually receding from us at speeds less than the speed of light. But if we think about what's going to happen 1 trillion years into the future, if we extrapolate and say, well, let's assume the universe is going to continue expanding, surely the distant galaxies are going to be so far away, moving at such ridiculous speeds, it's not going to be possible to image them. We're not in that position yet, but 1 trillion years from now, we will be. And it's interesting to think that if a civilization comes along on this timescale, if a civilization comes along on a timescale of 10 to the 12 years into the future, if they build themselves a Hubble Space Telescope and they look out and ask themselves, what is in the universe, and take a really, really long exposure, they will come to the conclusion, when they look out, they'll say, what's out there? They'll come to the conclusion, nothing, other than the stars in their own galaxy. They'll be able to see what's going on within their galaxy, but the expansion of the universe will be such that all the more distant galaxies will be receding from them so fast that they will simply not be able to see them. It's not a question of how good their technology is. It will simply be physically impossible for them to image galaxies once the universe has expanded 1 trillion years into the future. So no matter how advanced this technology is, this civilization that may come along in 1 trillion years' time, they will come to the conclusion there are no galaxies out there other than our own. It's interesting that we live in a time period such that we now know that we have the Milky Way galaxy and we know there are 1 trillion other galaxies out there. But given time, people will not be able to draw the same conclusions. A sobering thought. The universe is running out of hydrogen. I said in the beginning of everything that it actually takes about 3 minutes to make all the hydrogen in the universe. After the Big Bang, roughly speaking, after 3 minutes, all the hydrogen is there. And that's all the fuel you need for every star that's going to come along for the next 1 trillion years or so. However, 1 trillion years later, when you've been making stars for 1 trillion years and you started with this amount of hydrogen and you've been using it to make stars for 1 trillion years, the hydrogen starts to run out. Now, some people have said, somewhat contentiously, some people have said, maybe you can make stars out of something else. Do you really need hydrogen to make stars? Some people have said, well, what if you try and make stars out of something heavier? What if you take heavy elements and make stars out of that rather than take the lightest element, hydrogen? Some people have said, by putting the equations into a computer, maybe it's possible to actually get a star made from heavy gases such that there are fusion reactions in the core, but the surface temperatures turn out to be rather low, even lower than, for instance, the thousands of Kelvin of a red giant. It could be 10 times lower than that. Not thousands of Kelvin, but hundreds of Kelvin. It might actually be possible to make a star where there are fusion reactions in the core, but the atmosphere of the star could be low enough for ice to form. It could actually be 0 Celsius. You could actually make frozen stars. And no, that's the Disney version of a frozen star. That's not what I'm talking about. If that's the picture in your head, then let it go, because what I'm talking about is actually real physics that some people say nuclear reactions at the core, but ice on the surface. There are plenty of scientists who say rubbish. No, you can't do that. You absolutely need hydrogen for reasons I'm not going to go into. So there's a little bit of contention there as to whether or not that's the case. Let's assume that the majority are right and you do absolutely need hydrogen to make stars. So what's the consequence? Well, if we want to go any further than 1 trillion years into the future, we have to remind ourselves what's actually happening with the universe on the largest of scales. So we believe if we look at the size of the universe as a function of time, we are on one of these coloured lines, and we don't necessarily know which coloured line we're on. If we think of the relative size and where we are now, we're inside that circle. Notice that when we go backwards in time, how old the universe is depends on which of those coloured lines we're actually on. And each of those coloured lines depends on how much stuff there is in the universe, how much matter, how much energy. If there's a very large amount of matter in the universe, we would expect the expansion to increase, and then eventually gravity will win and the universe will get smaller again and we'll end up with a big crunch. And that means we live in a closed universe. But we don't think there's that much matter out there. When I was a nipper, it was thought that maybe we're on the green line. But now it looks like the best evidence we have is that actually we're on the red line. And what's actually happening is the universe has been expanding for 14 billion years and will go on expanding, and the expansion rate will increase because that line is getting steeper and steeper and steeper. It looks like maybe the acceleration is slowing down. There's some tentative evidence for that, but it looks like there's no sign of it wanting to simply come back and end up in a big crunch. So let's assume that we are on the red line and we're going to expand forever. So now notice I've changed the numbers at the top there. Now each box is 1,000,000 times further into the future, otherwise we're going to be here all night. And so we're talking about 1,000,000,000 years into the future, or a cajillion. I don't know what the adjectives are for these very, very ridiculously large numbers. But before this little aside as to what the universe is doing, I said it took 3 minutes to make all the hydrogen in the universe. But after 1 trillion years, the hydrogen is running out, and you need hydrogen to make new stars. Some stars can live a long time. Our sun lasts for 10 billion years. A really low mass star might last for trillions, or tens of trillions, or hundreds of trillions of years. But no star lives forever. So if the hydrogen runs out, what does that mean? One by one, all the stars will go out, and the age of starlight will come to an end. Whatever is left will still orbit around whatever galaxy it's in, the dead husk of a star. There will be a few of them drifting around like zombies. There will be white dwarfs, neutron stars, and black holes. Now, it might sound a bit odd to talk about white dwarfs not shining, but a white dwarf is simply the hot remains of the core of a star. It will cool off and it will go dark. There are no nuclear reactions in a white dwarf keeping them hot. They just start their lives hot and then cool off until they become black dwarfs, basically just lumps of carbon, not shining in the traditional sense that we mean. Some stars might get ejected from the galaxy, some stars might get eaten by the supermassive black holes at the center of the galaxies. Some magnetic fields have been mapped out. It's difficult to do it in our own galaxy, but in other galaxies we've mapped out the magnetic fields. For instance, SOFIA, the Stratospheric Observatory for Infrared Astronomy, the infrared telescope in the back end of a 747, that's been used to map out these magnetic fields, and we think that matter is funneled by these magnetic fields, and that's how the supermassive black hole at the core will end up eating the remains of the galaxy. And by the way, the 747 has just recently been retired, so watch out on eBay if you want one for yourself. It's going to be available. It's got a shutter. What's going to happen to all the atoms in the universe? Well, we're not actually sure what's going to happen to protons on a long enough timescale. We know that neutrons are unstable, but are protons unstable? Will they change? Well, it's protons, which are the charged parts of all atomic nuclei, Basically, all atomic nuclei are some combination of protons and neutrons. Protons are the charged particles. If they decay, then basically all atoms are going to fall apart. But we don't know if this is going to happen or not. If it does happen, it's not going to happen on a timescale less than about 10 to the 36 years. All evidence is that they are stable, but that simply means that we can't measure them on a long enough timescale. The calculations indicate that they should be stable on this timescale, maybe longer. If we assume that protons don't fall apart, and hence atoms survive for a little longer, well, unfortunately, that doesn't mean atoms are going to last very long, because the only atoms that exist are in these black dwarfs. There are none in neutron stars, there are none in black holes. So that if there are some atoms left in carbon atoms here in black dwarfs, eventually those stars evaporate via a mechanism I'm not going to describe. It's a quantum mechanical event. And therefore there will be no atoms in the universe on this sort of timescale. We're talking about ridiculous numbers now into the future. Black holes will merge, just like Andromeda is going to crash into our galaxy, and eventually those two supermassive black holes at the core will merge. That will happen in lots of galaxies in superclusters all over the universe. And so these supermassive black holes, which might start off as millions of solar masses, or billions of solar masses, are going to merge together, and perhaps you'll end up with monsters which could be trillions of solar masses, absolutely vast objects. But all the black holes in the universe will not last forever. They are not eternal. Black holes, we believe, evaporate. We can't prove that at the moment because we can't watch them for long enough to see it, but Hawking conjectured that all black holes evaporate, providing you wait long enough. So what's the mechanism? Why do we think that black holes evaporate? Well, there's a certain part of quantum mechanics that says you can always borrow energy from nothing if you so wish, and you can use that energy to make matter and antimatter, a particle and an antiparticle. In other words, borrow energy, make stuff, and that particle and antiparticle will annihilate and repay the energy. Again, you borrow energy, you make matter and antimatter, they annihilate, and you pay back the loan again. That, we believe, is happening all the time. The question that Hawking raised was, yeah, that's interesting, but what would happen if we apply that to the region just outside the event horizon of a black hole? What if you borrowed some energy? Let's imagine that's the event horizon. What if just outside that you borrow some energy, make a particle and antiparticle, and whoops, one of them goes into the black hole and the other one doesn't? You're left with an imbalance. It looks like the black hole has actually spat something out. It's not coming from inside the event horizon. It's a mechanism which results in something that looks like the black hole is losing energy. And if you do the calculation, you can calculate that all black holes will go through this process and will ultimately radiate away their entire mass. In other words, they will evaporate, they will shrink. We're now calling it Hawking radiation. As far as we know, it looks like the radiation increases with decreasing mass. So in other words, large objects will radiate very slowly. As they get smaller and smaller and smaller, they'll radiate more and more and more, and they will evaporate in a flash of radiation. So to start with, it'll be very difficult to see. That's why we can't tell if this is real or not. We can't look at any black holes that we know about and say, is there Hawking radiation coming off? Because they're far too big and the Hawking radiation is far too weak. But given long enough, we think this is ultimately what will produce the evaporation of all black holes. And notice we've got to the right-hand edge now. Even supermassive black holes, even the most massive supermassive black holes, will evaporate as long as you wait for a really, 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 really long time. So have we reached the end of time? Well, certainly I've run out of red rectangles here. Let's imagine that we take a number like 10 to the power 100, which is a googol. Not that Google, that's a different Google altogether. That's a misspelling of the original mathematical Google. 10 to the power 100 is a Google. And it's been calculated that after a Google years, there should be nothing left. Every black hole in the universe, no matter how massive it could have got, will have evaporated by this time. And so after this point, nothing happens because there's nothing left other than the radiation that the black holes produced. So at this point, time becomes pretty meaningless. And I don't usually do it, but let's just write out what a googol actually looks like so you can see how stupid it is. 10,000 million, you can do it yourself. It's a very long period of time. Just because we can't imagine how long that is, doesn't mean we can't do the maths and calculate what's going to happen on these timescales. There's a certain disconnect between our ability to imagine long time and our ability to do the calculations to see what is going to happen. So have we reached the end of time? Well, Woody Allen once said, eternity is a very long time, especially towards the end. But I like the XKCD version of trying to put the human perspective on these ridiculous timescales. They say a human is a system for converting dust billions of years ago into dust billions of years from now via a roundabout process, which involves checking email a lot. That's one way of thinking about the human condition. But given I've had my hour and I don't want to leave you too depressed, let me just finish with a very short epilogue. You could say that we live in a golden age because the sun is middle-aged and stable and well-behaved. And the moon's at just the right distance to stabilize the Earth's axis and hence stabilize the seasons. And as a little bit of a bonus, it's just the right distance to give us a total eclipse of the sun every once in a while. And thanks to evolution, we're able to explore, we're able to discover, and we're able to understand the universe in which we live. And we can do that by building machines that we can send out into the solar system and explore our nearest neighbors. And we can build machines like telescopes that can peer out into the universe and see billions of galaxies at distances of billions of light years. But we couldn't have done this in the early universe because we needed generation upon generation upon generation of stars to turn hydrogen into helium, helium into carbon and nitrogen and oxygen and calcium and phosphorus and iron, and all the elements that we need to make us us. And as we've just seen, in the future, trillions of years from now, the universe is going to be very dark and very boring. So you could say the best time to exist is now. Thank you all very much.